1.5, Parent Functions and Transformations. These are on your online textbook on pages 45 and 46. It's at the very beginning of the section, but I really like to go through them in detail because not all Algebra 1 and Algebra 2 teachers make a big deal out of graphing by hand. And the problem is we really need to be able to do that. We need to understand how graphs work. And if we're always making just tables, or if we're turning to technology like a graphing calculator or Desmos, we don't really understand the way that these work. So for a constant function, we mean when f of x just equals a constant like c. And so what we get in that case, think of this as like y equals a number, is we get some kind of horizontal line. So in this case, my horizontal line would be at c on the y-axis, and so that's f of x equals c. Identity function is just really talking about linear functions, but the identity function is the most simple form of a linear function, which is f of x equals x. So notice I don't have any number listed for slope here. My slope is just 1. My y-intercept is 0. So that's before I have translated that graph at all. So it goes through my origin, and it's going to be up 1 over 1. It's going to look like that. So when I am moving my graph up and down by changing my y-intercept, that's really translating it vertically, and we'll look at those in a minute. If I put a number in front of x and I give it a slope, I'm really stretching it or shrinking it. So that's going to be a dilation. And we'll look at that in a minute as well. So for quadratic, that's going to be of the form f of x equals x squared. So parent functions are really the most basic of each kind of function. They're mostly through the origin. If you think about like f of x equals x, or if I think about a quadratic function or a cubic function, where they're going to be kind of centered around the origin, and we haven't translated or moved them or stretched them or shrank them or done anything. So it's just the most basic form. My quadratic function, I know my vertex is at 0, 0. I go up 1 over 1, up 3 over 1, up 5 over 1. We have that 1, 3, 5, 7 pattern. And again, some teachers don't spend a lot of time on that pattern. So if that's new to you, you might need to get some extra support and work on your graphing this year. Cubic would be f of x equals x cubed. So you can kind of memorize what this one looks like. A lot of people don't. It's also really easy to just kind of cube numbers in your head. I know I'm going to have 0, 0. If I take 1 to the third power, I get 1. 2 to the third power is 8. And then if I raise a negative 1 to the third power, it's negative 1. Negative 2 would be a negative 8. And I get that cubic shape. I did not connect those dots very well. I apologize. Next, we have a square root function. So f of x equals square root of x. There's two really cool ways to graph this. The first is just think about numbers I can square root. Square root of 0 is 0. Square root of 1 would be 1. Square root of 4 would be 2. Square root of 9 would be 3. The other way I can think about that is I really have half a parabola. Parabolas have a 1, 3, 5, 7, and that's what I have here. I have up 1 over 1, up 3 over 1, up 5 over 1. It's just tipped on its side again because square roots and quadratics are inverses. So remember, an inverse would be reflected over that line, y equals x. So that's why I'm like switching the x's and y's around. Instead of graphing it around the y-axis, I'm graphing it around the x-axis because it's the inverse. For reciprocal, we have f of x equals 1 over x. The way I prefer to graph these is I think of it as y equals 1 over x, and I multiply both sides by x. So I have xy equals 1, and then I know a number times itself equals 1. I'm looking at a number and its reciprocal. So the easy point on here is that I know that if x is 1 and y is 1, that would be a point. 1 times 1 is 1. And now I think about numbers and their reciprocals. So that would be like 1/2 times 2, or 2 times 1/2, or 3 times a third, or 1/3 times 3. Those would all be a number times their reciprocal. So 2 and 1/2 would be right here. 1/2 comma 2 would be right here. So we get one of those branches. And now I could think about how negative times negative is positive. And so if I made all those points into negatives, I would still have points that worked. And so I'm going to be graphing kind of all these same points over in quadrant 3. So there's our reciprocal function. I want to graph absolute value next. I just put it on the right because I felt like that gave me more space underneath for greatest integer. So absolute value is f of x equals absolute value x. We know that we start at the origin, and we have a pattern of up 1 over 1. I can remember that the pattern is a bunch of 1s because the absolute value sign looks like a 1 to me. And last is the greatest integer function. The other name for this is the floor function. And your textbook uses these fancy brackets that look like this, not like the fancy brackets I normally call fancy brackets. So these are almost like a double bracket. Okay. And just to give you an idea about what greatest integer means, they define it as the greatest integer less than or equal to x. I think that is a super confusing thing to talk about it being a greatest integer and less than all at once. And so what I prefer to think of it as the rounding down function. This is going to round down to the nearest integer. That's what it's really going to do. So let's just look at evaluating a couple of these really quick. If I have, if I'm finding the greatest integer of, I meant to put an 8 in there. Let's do 8. Let's say a negative 8. So whenever I have an integer, it's just going to be the same thing. If I am doing this function and applying it to like 6.3, because it is a decimal or a fraction, it's going to round it down to 6. If I'm looking at something like 0.5, it's going to actually just round it down to 0. If I look at something like negative 1.5, it's going to round that down to negative 2. So the way that this works is I'm going to make an open circle here at the 1 and draw it back towards the origin and make that a filled in circle. So this is all where y equals to 0. That's where this line is. The line is at y equals 0, and these values show for x it gets really close to 1 but doesn't equal 1, all the way down to 0. Any of those values are just going to be known as 0. So now I need to think about what happens when x is all the way from 1 up until 2 but not quite 2, and that's going to equal 1. And then I need to think about how for x, if I am from 2 to 3, but not quite 3, that's going to get rounded down to 2. So for y equals 2, I'm going to put that row in. And then once we do a couple of these, we can kind of see the pattern. It's really hard to draw this on this little tiny graph and get it to work. See, that already doesn't look like an open circle, so we're going to go back and fix that. It's hard to draw them big enough. When I draw them really big to make them open, then they become kind of obnoxious looking. But that's how that function's going to work. So you've got the open circle and the closed circle, and they're connected. So now we're going to look at all the different kinds of ways that we can manipulate graphs. A lot of these are going to be review, but some of them will be new as well. So we're going to work a lot more in the horizontal direction than we typically have done. So for vertical, we know if I have a function g of x, it's going to be, and if we have like an f of x, so this is going to be like my parent function, and we add a number on the outside, we know it's going to move at k units up or down. And so I just thought we would do a quick graph to show that. Let's go ahead and graph f of x equals x plus 5. So that means I would start, instead of my original identity function that goes through the origin, and that would be my identity function. Instead, I'm going to move up 5. And then I'll graph my slope, up 1 over 1. So you can see the functions are the same. It's just been moved up 5 units. So if I want to move something horizontally now, Let's go ahead and write it out. Then I need to put whatever that is on the inside with the x of my parent function. So if my parent function is f of x, this would be f of x minus h. And it's going to move h units right or left, but it's always opposite in sign. H units right or left, and it's opposite in sign. So for this one, I always think about like a parabola. So if I'm graphing f of x equals quantity of x minus 1 squared, you can see that I have a minus 1 in the parentheses with the x, and so it is going to move it the opposite direction. This is going to move it 1 unit left. So when we are looking with the x, we're always doing the inverse. So that means instead of having my parabola at the origin, I'm going to move it 1 unit to the left, or sorry, 1 unit to the right. You know what? I screwed that up. Let's go back and fix it. I made a big deal out of opposite sign and then I screwed it up. So it's going to move it 1 unit right because it says minus 1. And then I'll go up 1 over 1, up 3 over 1, up 5. I think 5 would be up here, not there. Let's fix it on the other side. And then graph my parabola. For reflections in the x-axis, and this is what we've done before, just means over the x-axis. That means I would have something where if my parent function was f of x, I have a negative on the outside of it. And so the obvious one again is parabolas, but we've already done one of those. So let's go ahead and use the example that, let's say g of x equals negative of the square root of x. So that would mean instead of the square root of x, which would be up here, it's going to reflect that underneath. So this is going to reflect in the x. So I would start here and I would go 1 and then 3 and then 5. So that would be my new function. Now I'm going to show something that's reflected in the y-axis. So for that, let's go ahead. That would be like g of x. And so this time, instead of on the outside of my f of x, it's going to be on the inside. So f of negative x. So let's go ahead and look at, let's see, what kind of function haven't we done yet? You know, we could probably just look at a square root again, because then we could be comparing the two on the same page. So let's make this the square root of negative x. So if my square root function is normally over here, but I need to reflect in y, that means my function is going to go to the left now. 1, 3, 5. So that's reflections. Next page, we're going to look at dilations. So for dilations, it's when we're stretching or shrinking is what's going on. So if I am looking at a vertical dilation, that would be when I have the a being multiplied on the outside of that function. And that's going to be stretched by a factor of a. And really it could be stretched or shrunk, right? Depending on how big a is. So it's going to make it bigger if that factor is greater than 1. Remember, we don't have to worry about negatives here because negatives would be reflecting it. So if it's bigger than 1, it's going to make it bigger. If it's compressed, that means a is going to be between 0 and 1. Because if it's anything less than 0, it's reflected. There's all other kinds of things going on. So we're looking at a being an absolute value. Horizontal are expanded and compressed are going to be backwards. g of x will be equal to f of ax. So in order to do horizontal, we have to go inside the parentheses with the x instead. And this one does the reciprocal. And so like I've already told you here, the expanded and compressed are going to be backwards from each other. It does the reciprocal. So whenever I do the vertical, it's multiplying, it's doing exactly what it says. When I'm doing the horizontal, it's really the inverse. So if I was adding a number to x, I'm really moving it in the negative direction. If I'm multiplying it by something, I'm really multiplying it by its reciprocal, so the inverse instead. So we'll look at a couple examples here. I think for this one, we'll do absolute values. So for this one, I'm going to look absolute value of, I'm just writing y, I'm getting lazy. So let's do 2 times absolute value of x. So that 2 is going to multiply my pattern in the y direction. So I'm going to start here. I'm still going to go over 1, but I'm going to go up 2 each time. For horizontal, I think I'll do another square root. I don't think we've messed around a lot with those. So for this one, I'm going to use y equals the square root of, we'll do 2 again, just because it's easy. So this is going to mean that we're really compressed by 1/2 horizontally. Compressed by half. Okay, so instead of over 1 unit and up 1, I'm going to go over half and up 1. And then instead of over 4, and oh, we have to start at 0, 0 still. If instead of going over 4 and up 2, I'm going to go over 2 and up 2. And then the next one would be like 9, 3. So instead of over 9 up 3, I'm going to go over 4.5 and up 3. So what I have done is I've compressed this down. I've taken that original function, which might be worth graphing as well. And I've taken each of those values and I've divided them in half. So instead of this point being way out here at 9.3, now it's at 4.5, 3. This one, instead of being at 4.2, is now at 2.2. So I have compressed that horizontally. Our last step is going to be graphing a piecewise function. So when I graph piecewise functions, I'm looking at all these different restrictions on x. So first it says absolute value of x plus 2 if x is greater than 0. So let me see if I can find a highlighter. And what that means, less than 0, would be this entire region over here. So over in this region, I am only going to graph that function, absolute value of x plus 2. And we'll do that with a blue line because I already have it circled in blue. So that would mean I am shifting my absolute value 2 units to the left. And then my pattern's 1, 1, 1. When I get to this line, I stop. And then we need to think about, is it less than 0 or is it less than or equal to 0? And it says less than 0. So I need this one to be an open circle. Now I need to look at the middle part, absolute value of x minus 2 from 0 to 2. So let's go ahead and highlight from 0 to 2. You don't have to highlight, but I find for beginning graphing on this stuff, it really helps. Now this one, I see that they're both or equal to. And so when I graph them, it's going to get solid filled in points on both ends. And I kind of feel like it should all be in one color because it's one function. So I am going to switch back to blue again. I don't want you to think this is 3 different functions. It's 3 parts to the same function. So absolute value of x minus 2, like this, would mean that I am moving my absolute value down 2. And I would need to go up 1 over 1 on both sides, but I can't go to the left because that's where it's yellow. So I'm only going to go in the pink zone. So this part of my function is just going to be that little line. My last part says I'm taking the square root function and I'm moving it 2 units to the right and then 2 units up. So let's go ahead, and that's going to be in our last region. but I'm going to highlight it anyway. So that function we're going to put over here. Again, the highlighter is not necessary. If I was in class with you and using paper and pencil, I'd probably have you use colored pencil to shade it, but it's really not necessary. I think it's just helpful for beginning graphers. So I've got to think of a square root graph. Instead of starting in the middle, it would be going 2 units right and 2 units up. So this is going to be like my new 0. And then I'm just going to think about that square root pattern, which is still just the 1, 3, 5, 7, just half of a parabola. So 1, 3, 5, and then go ahead and connect. Oh, but this should be an open circle right here, shouldn't it? So let's go ahead and put an open circle there instead. That is the end of our piecewise function graphing. Please come to class if you've got questions. Thank you.